Hi, good evening, everybody. Welcome back to my lecture classes on life sciences. And today we're going to deal with the fifth topic, that is, of the 10 topics in life sciences. First topic of molecules and their interactions relevant to biology. We're on the first, second, third, fourth, fifth aspect of bioenergetics glycolysis, oxidative phosphorylation, coupled reactions, group transfer, biological energy transducers, right? So today I'm just giving a full coverage on that particular topic, and then towards the weekend, from now on, right? Okay, we're trying to cover one topic each day, and at the end of the week we'll have a questionnaire session where I'll give you questions at the end of the week, and you answer these. Listen to my lectures and you answer the questions, right? So you need to know that. You get, and once we finish almost a month into that, we'll have MCQs. Right? You can log into my WhatsApp line, and I'll give you the questions and the MCQs. You have my Google Meet as well. It's there on the thing. You can use my Google Meet link, and which will be displayed on the WhatsApp. And you answer the question. It should be good, and it could help you a lot, right? So today we're on to bioenergetics, the concept of free energy, right? So energy, some basic principles about it, right? The two concepts most basic to science are matter and energy. So you know that. So we shall introduce these concepts by defining matter as anything that has mass and takes up space, right? So energy, however, is more abstract. It can only be described and measured by how it affects matter. You can recall that energy is the capacity to do work, right? And that is to move matter against opposing forces, such as gravity and friction. Put it another kind of way, its energy is the ability to change the way a collection of matter is arranged. Arrange, rearrange, set, reset. Higgs boson theory about matter, and various theories into that. And of course, the various forms of energy. That's anything that moves possesses a form of energy called kinetic energy. Any moving object, including an atom or molecule, has kinetic energy. The energy of motion is called kinetic energy. Moving objects perform work by imparting motion to other matter. A pool player uses the motion of the cue stick to push the cue ball, which in turn moves the other balls. Water gushing through a dam turns the turbines. Electrons flowing along a wire run household appliances. The contraction of leg muscles pushes bicycle pedals, right? These are all kinetic energy aspects, various incarnations of kinetic energy. You have heat and thermal energy is kinetic energy that results from the random movement of molecules. Light also represents energy which can be harnessed to perform work such as powering photosynthesis in green plants. A resting object not presently at work may also possess an energy which is the capacity to do work. Right? So stored energy or energy or potential energy is energy that matter possesses because of its location or arrangement. Water behind a dam, for instance, stores energy because of its altitude. Chemical energy, a form of potential energy especially important to biologists, is stored in molecules because of the arrangement of the atoms that are bonded together. Right? And next topic of interest would be energy transformation. So energy can be converted from one form to another, right? So chemical energy can be tapped when chemical reactions rearrange the atoms and molecules in such a way that potential energy is stored and the molecule is converted to kinetic energy. This transformation occurs, for example, in the engine of an automobile, when the hydrocarbon of gasoline reacts explosively with oxygen, releasing the energy that pushes the pistons. You've heard of a combustion engine, right? This is what happens in it. So similarly, chemical energy fuels organisms, cellular respiration and other anabolic pathway unleash energy stored in sugar and other complex molecules and make that energy available for cellular work. The chemical energy stored in fuel molecules is itself converted from light energy by plants during photosynthesis. All right? And about the free energy concept, a criterion for spontaneous change. How can we predict what can and cannot occur in nature? How can we distinguish the possible from the impossible? We know from experience that certain events occur spontaneously and others do not. For instance, we know that water flows downhill, the objects of opposite charges move toward each other. The ice cube melts down at room temperature and the sugar cube dissolves in water. So explaining why these processes occur spontaneously is a bit puzzling, right? So let's start with defining a spontaneous process as a change that can occur without outside help. A spontaneous change can be harnessed in order to perform work. The downflow of water can be used in turn to move a turbine to power a plant. That's for example. And a process that cannot occur on its own is said to be non-spontaneous, right? So that happens only if an external energy source is added. So water moves uphill only when a windmill or some other machine pumps the water against gravity, and a cell must expend energy to synthesize a protein from amino acids. So that's a non-spontaneous becoming a spontaneous action. A catalyst kind of move in it. It's not exactly a catalyst, but it's a push factor. Of course, catalyst is a push factor. It's actually a combustion factor, right? Catalyst speeds up a reaction. Here we have an energy, external source of energy moving it, the kinetic energy that moves it to cause it, right? So when a spontaneous process occurs in a system, the stability of the system increases. Unstable systems tend to change in such a way that they become more stable. A body elevated by a column of water, such as a reservoir, is less stable than the same water at sea level. So you raise it up, the energy builds up, that is able to push down, right? There's force. That's what happens in a dam. You take it to a height, pours down, it turns a turbine, it generates electricity. In that case, it's electricity. So potential energy can become kinetic energy and then can become electric energy. That's how it transforms. So the energy transformations, right? So when a spontaneous process occurs in a system, the stability of the system increases. Unstable systems tend to change in such a way that they become more stable. A body of elevated water, such as a reservoir, is less stable than the same water at sea level. So a system of charged particles is less stable when opposite charges are apart than when they are together. In situations less familiar to us, how else do we predict which changes lead to greater stability in a system? That's another question to be answered, right? So which changes are spontaneous? The concept of entropy teaches us that any process can occur only, or it cannot only occur spontaneously if it increases the disorder of the universe. It's a general concept of entropy, right? Let me repeat that. This concept of entropy teaches that a process can only occur spontaneously if it increases the disorder of the universe. This principle is helpful in theory, but it does not give us a practical criterion to apply to biological systems because it requires that we measure changes in the surroundings. So we need some standard for spontaneity that is based on the system alone. The criterion is called free energy, right? So the concept of free energy is not easy to grasp, but therefore it is worth the while because the idea can be applied to many biological problems, right? Now, if you see free energy, it is the portion of a system's energy that can perform work when temperature is uniform throughout the system, as in a living cell. A system's quantity of free energy is symbolized by the letter G. There are two components to G. The system's total energy is symbolized by H, and its entropy symbolized by S. Entropy was symbolized by S. Free energy is related to these factors in the following way. G, capital G, is equal to H minus Ts, right? Write that down. T stands for absolute temperature. So a system's quantity of free energy is G, right? Capital G is equal to total energy H minus T is the absolute temperature times the entropy, which is symbolized by S. So right. So a degree centigrade or degree Celsius plus 273. That's T stands for absolute temperature, degree centigrade plus 273. Notice the temperature amplifies the entropy term of the equation. This makes sense, right? So as we learned earlier, temperature measures the intensity of random molecular motion heat, which tends to disrupt order. So what does this equation tell us about free energy? Not all the free energy stored in a system is available for work. The system's disorder, the entropy factor, decreases the availability of energy to perform their work. All right, now how does the concept of free energy help us determine whether a particular process can occur spontaneously? Think of free energy, G, in the above equation, as I've just now mentioned to you, as a measure of a system's instability. Less its tendency to change to a more stable state. Right? Systems that are rich in energy, such as stretched springs or separated charges, are unstable. So are highly ordered systems, such as complex molecules. Thus, those molecules are those systems that tend to change spontaneously to a more stable state are those that have a high energy, lower entropy, of both. The free energy equation weighs these two factors, which are consolidated in the system's G content, free energy content. Now we can state a versatile criterion for spontaneous change. That is, in any spontaneous process, the free energy of a system decreases, right? The change in free energy as a system goes from a starting state to a different state is represented by uppercase delta G, which is equal to free energy in the final state minus free energy in a starting stage. That is G, final state, minus G, starting stage. So put it another way, delta G, that is uppercase delta G, is equal to delta H minus delta T, T delta S. Okay, minus temperature into delta S, right? T stands for absolute temperature in Kelvin units, K degree centigrade, K. And degree Celsius plus 273 is the Kelvin, is the equivalence factor. And for a process to occur spontaneously, the system must either give up energy, decrease in H, give up order, and increase in H, or both. When these changes in H and H are tallied, delta G must have a negative value. That is, the change in free energy as a system going from starting to a state to a different state, which is represented by delta G, must have a negative value. The greater this decreases in free energy, the greater the maximum amount of work the spontaneous process can perform. This is a formal mathematical way of stating the obvious. Nature runs downhill. Downhill in the road metaphorical sense of a loss in useful energy minus the capacity to perform work. Okay, now to the two laws of thermodynamics. Okay. The study of the energy transformation that occurs in a collection of matter is called thermodynamics. Let me repeat that for you. The study of the energy transformation that occurs in a collection of matter is called thermodynamics. Researchers around the world used the system to denote collection of matter under study and refer to the rest of the universe as everything outside the universe as the surroundings. A closed system, such as that approximated by liquid in a thermos bottle, is isolated from surroundings. In an open system, energy can be transferred from between the systems and its surroundings. So organisms are open systems. Organisms are open systems. They absorb light energy or chemical energy in the form of organic molecules and release heat and metabolic waste products such as carbon dioxide to the surroundings. It's an open system of free energy. According to the first law of dynamics, the energy of the universe is constant. Energy can be transferred and transformed, but cannot be created or destroyed. The first law is also known as conservation of energy. The hydropower station does not create energy but converts potential energy stored in water into electrical energy when falling water moves the turbines. Right? The law of thermodynamics can be stated in many versions. To begin with, let me repeat that again for you. The second law of thermodynamics can be stated in many ways. To begin with, the following concept would explain things better. That's every energy transfer or transformation makes the universe more disordered. Right? If everything stands still, it's preserved. So there is a quantitative measure of disorder, which is called entropy. So basically, entropy is the quantitative measure of disorder, which value increases or whose value increases as disorder increases. So entropy is directly proportional to the disorder of change, or disorder changes, or the increase in disorder, a disruption. We can now state the second law as follows. Every energy transfer or transformation increases the entropy of the universe. I repeat, every energy transfer or transformation increases the entropy of the universe. There is an unstoppable trend towards randomization. In many cases, increased entropy is evident in the physical disintegration of a system's organized structure. Consider, for example, the degradation of an unmaintained building. Much of the increased entropy of the universe is less apparent, however, because it takes the form of an increasing amount of heat, which is the energy of random nuclear molecular motion. In most energy transformations, all the forms of energy are at least partly converted to heat. Only 25% of the chemical energy stored in a fuel tank of an automobile is transformed into the motion of the car. The remaining 75% is lost from the car engine. As what? As heat. Right? So which dissipates rapidly through the surroundings. Right? In performing various kinds of work, Living cells unavoidably convert organized forms of energy to heat. This makes a room crowded with people uncomfortably warm. So it's more people, there's more temperature, it becomes uncomfortable. In machines and organisms, even energy that performs useful work is eventually converted to heat. The organized sector, the organized energy of an automobile's forward movement becomes heat. When the friction of the brakes and tires stops the car, conversion to heat is the fate of all the chemical energy. Conversion of other forms of energy to heat does not violate the first law of thermodynamics. Energy has been conserved, because heat is a form of energy, although in its random state. On combining the first and second laws of thermodynamics, we conclude that the quantity of energy in the universe is constant, but its quality is not. In a sense, heat is the lowest grade of energy because it is an uncoordinated movement of molecules that many systems cannot harness in order to perform work. A system can only put heat to work when there's a temperature difference that results in the heat flow from a warmer location to a cooler one. So if temperature is uniform throughout a system as it is in a living cell, then the only use for heat energy is to warm a body of matter such as an organism. Thus, an organism takes in organized forms of matter and energy from the surroundings and replaces them with less ordered forms. For example, an animal obtains starch, proteins, and other complex molecules from the food it eats, and in turn, it releases carbon dioxide and water, relatively small and simple molecules that show less chemical energy than the food. The depletion of chemical energy is accounted by heat generated during the metabolism. Cells create ordered structures from less organized starting materials. For example, amino acids are ordered into the specific sequence of polypeptide chains. Complex organisms evolve from simple ancestors, but this high degree of organization in no way violates the second law, because the entropy of a particular system, such as an organism, may actually decrease as long as the total entropy of the universe, the system plus its surroundings, increases. Thus, organisms are islands of low entropy in an increasingly random universe. The evolution of biological order is perfectly consistent with the laws of thermodynamics. Right, so that's the first portion. And we move into the second portion, which is called the thermodynamic principles in biology. Right, now we're on to the second portion, that's thermodynamic principles in biology. So free energy change, we consider a system consisting of two components, A and B, which react to give C. That's A plus B given C. By reacting, the system can change work or energy, that's heat or light, with the immediate surroundings. For instance, it can receive energy and produce an equivalent amount of work. So at the time of mixing, A plus B represents the initial state, and C, the product formed, represents the final stage. Simple explanation, as simple as it can get. Each of these two states is characterized by an internal energy level, U1 and U2, respectively, which depends on the chemical nature of the constituents, right? Which the atoms, the bonds, the concentration, and the position in space, absolute temperature T, pressures P, and volume V. So the internal energy change denotes by AU, resulting from a change in molecular structures, new bonds, and different distributions of electrons. which depends on the initial state and final stage. AU is equal to U2 minus U1, right? U1 and U2 are the characterized by the internal energy levels, two states. It's the maximum quantity of energy which can be made available to accomplish a work by the transformation of A plus B into C. In a constant pressure system, as in the case of many biological reactions, there can be volume changes and either a liberation or an absorption of heat. Hence, the work done by pressure is equal to P, that's pressure, into V2 minus V1, that's P delta V. The best of it that can be expressed is the heat of reaction, first defined by AQ, is equal to internal energy change plus the work done. So delta Q, uppercase delta, capital Q, is equal to uppercase delta U plus P, uppercase delta V. All right? That being said, for a given temperature, because we know that PV is equal to small nRT, where N is equal to a number of moles, R is equal to gas constant, T is equal to temperature in degrees Kelvin. So delta H is the enthalpy change, enthalpy I said. Change of the system. Delta H, like delta Q, is mostly expressed, in calories or kilocalories per mole. But ought to be expressed in joules per mole. That's 1 calorie is equal to 4.18 joules. So delta H can be measured in a calorimeter. If delta H is less than 0, the reaction is exothermic. Right? Where heat is liberated. And if delta H is greater than 0, the reaction is endothermic. The system absorbs heat. Okay, so what's delta H? I hope you remember that. Delta H is the enthalpy change of the system. Delta H, like delta Q, is mostly expressed in calories or kilocalories. And it's better expressed, ought to be expressed in joules per mole. All right? For quite some time back, it was thought that the knowledge of the sign of delta H is insufficient to predict whether a reaction is spontaneous or not, and it was said that an exothermic reaction is spontaneous while an endothermic reaction is not. It was then found that while these predictions are correct, most cases are exceptions. Most cases, if it is right for most cases, there are exceptions, and that some spontaneous reactions are in fact accompanied by absorption of heat by molecules. So there are certain exceptions. So it was therefore one was therefore led to consider the entropy of the system, denoted S, a function which measures the disorder of a system, and variations of which delta S is equal to S2 minus S1. Depends like delta U. On the initial state and the final state. In order to pass from a first stable state, the initial state, to a new stable state, the final state, and one must upset the structures of molecules A and B for the reaction to take place. The greater the increase in molecular disorder, the greater the entropy. For example, entropy increases while passing from a given protein to the constituent amino acids in free state. I repeat, entropy increases while passing from a given protein to the constituent amino acids in free state. So entropy is related to the complexity of the molecules. The larger the number of molecules, the larger the number of complicated chemical groups, the larger the number of possible structures, and the greater the entropy. In a reversible transformation at constant pressure, delta Q is equal to T delta H. One can thus write delta H is equal to delta G plus delta Q, which is equal to delta G plus T delta H. Or delta G, free enthalpy change, is equal to delta H minus T delta S. In a reversible transformation at constant volume, AV is equal to the free energy change, which is delta F equal to delta U minus T delta S. In biochemistry, it is admitted that in most cases delta V is equal to 0 because the volume change for reactions taken place in solutions are negligible. In equations 3, so equations that give which gives delta G, it is therefore admitted that P delta V is equal to 0, so that delta G becomes like delta F, and this is equal as formerly mentioned, and delta U minus T delta S, and therefore delta F becomes delta G. This is particularly true if the aspects involve liquids and solids in solution and no gas at physiological temperatures which are low. So 3 cases are possible. When delta G minus 0 is less than 0, the reaction is exergonic. It can be spontaneous and free energy is available. On the contrary, let me repeat that. On the contrary, if delta G is greater than 0, the reaction is endergonic. Free energy must be supplied to the system for the reactions to take place. The reaction will take place only coupled with another exergonic reaction whose negative delta G is greater in absolute value than the positive delta G of the endergonic reaction. Right? So various biochemical reactions are reversible. So that where delta G is equal to 0, when dynamic equilibrium is reached, this is very interesting because for very small variations of active masses of the reaction's participants, the reaction can take place in either direction without energy problems, as delta G will vary in either direction. It can be noted that if delta S is small, as T is comparatively low in biochemistry, the term T delta S can be neglected, and then delta G is equal to delta H. In other words, in this case, the term exothermic and exergonic on the one hand, and endothermic and endergonic on the other hand are similar. Note these terms, okay? You need them. And application of these to chemical reactions. If we consider 2 compounds, A and B in solution, at 25 degrees centigrade under a pressure of 1 atmosphere, each in a concentration of 1 molecule per liter, 1 mole per liter of solvent, that's 1 mole, MOL/AL, which can react completely given C plus D, which would therefore be present in the same concentration after total transformation. The free energy is called standard and denoted as uppercase delta G0. Alright? If delta G0 is less than 0, the reaction is exergonic. It can take place spontaneously, but this is not necessarily the case if the free energy change is very large. So, as a matter of fact, delta G0 expresses the free energy change between an initial state and a final state. However, delta G0 gives no information on reaction velocity. A catalyst, an enzyme, for example, might be needed to trigger the reaction and adjust its velocity without altering its thermodynamics. And its characteristics. Despite the highly negative value of delta G0, 686 kilocalories per mole of the total oxidation reaction of glucose, C6H12O6 plus 6O2 plus 6CO2 plus 6H2O, this substance can be left for years in the presence of oxygen of air without any oxidation taking place. Right? On the one hand, while AG0, that delta G0 indicates standard state, it does not take into consideration the special circumstances which may prevail, particularly in the biological medium and condition and activities of compounds, pH, etc. Normally, reversible reactions proceeds up to the equilibrium state, and delta G takes this equilibrium state into constant, but the reaction can proceed up to completion. If the equilibrium state is continuously broken because the reaction products are progressively consumed by a following reaction, this is what happens in metabolic chains. In fact, a general state of equilibrium is observed. On the other hand, reactions which at the limit can be reversible in vitro can be reversed in vitro because of metabolic conditions, whereas in fact, the free enthalpy change delta G or free enthalpy energy change delta F will always depend on metabolic circumstances and will be related to equilibrium states in vital. And for an equation, delta G0 depends on the equilibrium constant K of the reaction. Delta G0 is equal to minus RT per NK. And that in given circumstances, the effective delta G of a reaction is delta G equal to delta G0 plus RT ln parenthesis C parenthesis D by A and B. First factor and second factor, right? For a reversible reaction, A plus B is to and fro C plus D, proceeding from left to right. The delta G of the reverse reaction will have the opposite sign, right? As I finish, you write the notations for deltas, all the various notations given. As soon as I finish this, I'll redirect the camera onto the formulas, note them down, right? For a reversible reaction, as I just told, the reaction will have the opposite sign. The delta G, let me repeat that again, for a reversible reaction A plus B given and returning to C plus D, proceeding from left to right, the delta G of the reverse reaction will have the opposite sign. Hence, two factors define delta G. On the one hand, the delta G which characterizes a given reaction, and on the other hand, the second factor characteristic of given circumstances and hence related to concentration, activity, dissociation or protonation, or the reaction participants, etc. When the ratio of activities of the second factor becomes equal to 1, the second factor becomes 0, and delta G is equal to delta G 0. Right? So it ought to be noted that delta G and delta G0 correspond to pH, which is 0, and ambient temperature, while delta G and delta G0 represent the values in the physiological conditions, where pH near 7, physiological temperature is 30 to 37 degrees, to be specified in each case. So let's examine the case of a reaction whose delta G0 is equal to minus 3 kilocalories per mole. It is known that R is equal to 1.987 calories per mole per degree, and at 25 degrees centigrade, T at 273 plus 25 is equal to 298 degree Kelvin, and that in K is equal to 2.3 log K. We write delta G0 is equal to minus 3000 calories per mole, which is the equivalent of minus 1.987 into 298 into 2.30 log K. Therefore, log K is equal to minus 3000 by minus 1362, which is equal to 2.2. These are chemical calculations that you need to know about and which is done on various factors when you take these things into consideration. If on the contrary, a reaction has a delta G0 is equal to plus 3 kilocalories per mole, then K will be approximately equal to 0.01. In other words, the reaction will practically not take place because equilibrium will be reached as soon as only 1% of the reactants will have transformed. There's a table which I will show to you as soon as I finish. And it is clear that the reaction whose equilibrium constant is greater than 1, accompanied by a decrease of free energy. This energy becomes available. These are exergonic reactions. On the contrary, if K is less than 1, the reaction is endergonic. Fine? And it follows that the delta G0 of a reaction can be calculated if one knows K. Right? And one can measure the concentration of the reactants and reaction products, this which is possible except when K is extremely small or extremely large, right?